So, given a trigonometric identity, how do you decide how to verify this trigonometric identity? Well, there is a step 0 to all of this because this is a decision that you have to make before you even get started. What side do you start with? Ultimately, our goal is to turn one side of an identity into the other side of an identity. So step 0 is going to be start with the side that looks more complicated. The reason being, in the world of math, it is a lot easier to simplify things than it is to unsimplify things. As a result, I'm going to encourage you to start with the side that looks more complicated. Now, there is nothing that is going to work every single time, but there are a set of guidelines that you could potentially use. Number 1, express everything in terms of the sine function and the cosine function. Now, through the use of the reciprocal and quotient identities, this is always something that is possible. For example, let's say for the sake of argument that I give you the tangent of alpha plus the secant of alpha. Now, in the event that I give you this, and I say use the quotient and reciprocal identities to express this in terms of the sine and the cosine, this will be the sine of alpha over the cosine of alpha plus 1 over the cosine of alpha. What results is two fractions being added together that already have a common denominator. Then we could express it in terms of only one fraction. Speaking of fractions, you're going to see a lot of them in all of these problems. So strive to reduce the number of fractions. Now, by strive to reduce the number of fractions, I mean frequently when you're doing operations like this, you're going to wind up with multiple fractions. For example, we could consider the cotangent of beta times the, hang on, I got this, times the secant of beta. Let's say that I employ strategy number 1, and I want to express these in terms of sine and cosine. Well, the first one would be the cosine of beta divided by the sine of beta, and the second one would be 1 over the cosine of beta. At which point you can probably observe that the cosine of betas will cancel each other out, and you'll be left with 1 over the sine of beta. Or, potentially, you could express that as the cosecant of beta, something along those lines. Number 3. If you see squares, try a Pythagorean identity. For example, if I were to take the cotangent of gamma plus the tangent of gamma, I don't actually see any squares here. But if we employ some of our other basic strategies, this could be the cosine of gamma over the sine of gamma plus the sine of gamma over the cosine of gamma. If we get a lowest common denominator for these, our lowest common denominator is going to be the sine of gamma times the cosine of gamma, which means that I will need to multiply the first fraction by cosine of gamma over cosine of gamma. And I'll need to multiply the second fraction by the sine of gamma over the sine of gamma. This establishes our lowest common denominator. Then we can simply add the numerators together to get cosine squared gamma plus sine squared gamma. And I'm hoping that people recognize that that numerator is now a Pythagorean identity, and we could express that numerator as simply 1. Again, these are simply guidelines. They're not things that are going to work every single time in every single problem, but they're good strategies to have. Number 4. Don't forget about algebra. By this point, you've had elementary algebra, intermediate algebra, as well as college algebra, which means that you should be comfortable with certain algebraic techniques like foiling, distributing, factoring, things of that nature. As an example of something algebraic, if we had the cosine squared of theta divided by 1 plus the sine of theta. There is a Pythagorean identity for the cosine squared of theta, that the cosine squared of theta is equal to 1 minus the sine squared of theta. You'll notice that the numerator is now a difference of perfect squares. It is 1 squared minus the sine squared of theta. As I frequently say at parties, when I go to parties, which doesn't happen a whole lot because, it's supposed to stay inside, we can factor that difference of squares into binomial conjugates. You'll notice now that 2 of these terms will cancel each other out, 2 of these factors will cancel each other out, and you'll be left with 1 minus the sine of theta. Tends to be a little bit simpler. For basic strategy number 5, when all else fails, you can try multiplying by a conjugate. Now, I mentioned in the previous problem that a difference of squares factors into binomial conjugates. Let's say that I gave you that same problem, but instead of having a cosine squared of theta in the numerator, I just gave you a cosine of theta. Well, cosine of theta, we can't use a Pythagorean identity for that. So what I'm going to do is multiply top and bottom by the conjugate of the bottom. Conjugates only apply to things that are added or subtracted. A conjugate is simply switch the sign that's between them. This would leave the numerator with the cosine of theta times quantity, 1 minus the sine of theta. And your denominator is going to be 1 minus the sine squared of theta after you expand. I mentioned in the last example, 1 minus the sine squared of theta happens to be equal to the cosine squared of theta. As a result, you can cancel out some of the cosines, and you could express this as 1 minus the sine of theta over the cosine of theta. Or from there, you could even say 1 over the cosine of theta is equal to the secant of theta, and sine over cosine would be the tangent of theta. So all sorts of possibilities exist as far as how these things can be manipulated. Strategy number 6 is going to be eyes on the prize. And by eyes on the prize, I mean you know what your final answer is supposed to be as soon as you complete step 0. You know what you're supposed to try to be turning this into. So with that in mind, if you see that there are fractions, try to bring in some fractions. If you see that there are no fractions, try to get rid of fractions. There's always a strategy if you remember what your goals are. And finally, while I tried to give you a pretty comprehensive list of all of the strategies just now, not everything is going to work every single time. Now, it may happen that you're working on these problems and you get a little bit discouraged because things that you're trying are not working. I read somewhere on the internet that being terrible at something is the first step toward being really good at something. and it's true. The only reason that I'm really good at verifying trigonometric identities is that I failed at them a bunch of times when I first started doing them. So, don't give up. Keep trying things. I've had students in the past come to me and say, Professor Friday, I don't know how to do this trigonometric identity. And I'll say, okay, well, what have you done so far? And they say, nothing. And I said, that is why you fail. You got to try something. Do something. Keep trying things.